Hi, everybody. Welcome to this talk about a failure mode you didn't know you had, maybe, noisy neighbors. You might be familiar with one of these surveys. This one was published by Datadog, which shows that for many of the containers that we run, they utilize a lot less than the requests that we provide to them. And so I want to start with running a similar survey here. We have a lot of people, so let's try this. So can you please raise your hand if you know the CPU utilization of a production cluster with user-facing traffic? Raise your hands. Okay, a fair bit of people. Keep your hands up. You know the CPU utilization, so leave your hand up if it's over 20% CPU utilization. Okay, most hands are still up, but some of them fell. More than 30%. Okay, another maybe 30%. 30% down. 40%. Okay, now most of the hands were retracted. We still have a few. More than 50%? Oh, you're a brave person. I want to talk to you later. So if you said between 20 and 40%, you're in good company because some of the world's largest companies that are capable of optimizing their systems, obviously, have reported CPU utilizations of between 20 and 40%. But what happened in the last few years is that some companies were able to achieve a lot better efficiencies. And for example, Google reported 35% in 2011 and up to 50% in 2019. That's a 1.5 times better utilization in their clusters. It's very significant. So what happened around that time? By the way, is the presentation visible with all the lighting on me? Can you see the slides okay? All right. So what happened over the last few years is I've been able to find two major contributors. One of them is advancements in vertical auto-scaling, where the system can correctly size the requests, the memory and CPU requests, so that Kubernetes can, or in those cases, other orchestrators, but your orchestrator could fit more containers onto the same number of systems, and you can run at higher density. But it requires another major contributor, which is handling the performance interference or noisy neighbor between these systems. If you're trying to run at higher density, you really need to tackle these performance problems for your system to behave correctly. And these capabilities were not developed in secret. Over the last more than a decade, there have been dozens of papers from well-known research universities and your hyperscalers detailing techniques on how to handle these noisy neighbors. And I think there's enough knowledge out there that we can create systems for the Kubernetes ecosystem that can be useful for everybody. And so in this talk, I'd like to cover the noisy neighbor problem. I'll talk about why this is happening and do I actually have it in my cluster? Should I bother solving it? Should I care? If I care, what can I do to actually solve the problem? And then talk about the open source efforts that we're expending now. I did my PhD in noisy neighbor mitigation, specifically network noisy neighbor mitigation. I then founded a company called Flowmill, which developed an eBPF-based network monitoring solution that we later sold the company to Splunk and open sourced the code, and it's now part of OpenTelemetry, the OpenTelemetry network collector, and I'm still a maintainer, and I'm now working on noisy neighbor mitigation. So let's talk about what is noisy neighbor. We deploy these cloud-native apps, but ultimately they run on physical hardware, these servers, and they have to share the physical resources that the servers offer them, and those resources are constrained. If one application uses more than its fair share of resources, then other applications cannot access these resources, and so their performance degrades. In this talk, I'm going to focus on one resource that is relatively important, and a lot of people don't know that we have this problem, which are the memory subsystem. And I'm going to talk about last level caches, which I'm just going to call caches, and memory bandwidth. So how does a cache noisy neighbor look like? A regular application might fit into the memory hierarchy like this. In purple there, you have the blazingly hot working set that fits into L1. Then you have the hot, warm, and cool working sets that fit into L2, L3, and DRAM. When a noisy neighbor comes in, it reads and writes a lot of memory and uses the last level cache, the L3 cache, very, very aggressively and evicts your application out of L3 cache. And so now your application, in order to access its warm working set, has to go to DRAM. In the more extreme example of cache noisy neighbor, that noisy neighbor sits next to your application on the same physical core as another hyperthread. And so it also uses L2 cache and evicts your application out of L2 cache. And now your application, even for the hot working set, needs to go to DRAM. And if you look at the access times above there, the difference between L2 cache and DRAM can be massive, more than 50 times in some cases. And so theoretically, this shows that there could be a major degradation in performance when you have this type of noisy neighbor. Does this happen in practice? Google ran a test on their production workloads, measuring slowdown in the face of different noisy neighbors. And they found for web search, which is the Google search node, the production Google search node, they found a 5 times degradation in latencies when faced with noisy neighbors, with DRAM and cache noisy neighbors. ML Cluster is a machine learning text classification system that works on user requests in real time. That suffered 5x. And then memkeyval is a key value store in memory like memcache, suffered up to 14 times slowdowns. Okay, so these are synthetic benchmarks, and the noise generator is not something that you'd see on real system unless you're running some big data analytics next to your production workload, which you shouldn't. Obviously, this tells you. Does this happen if I'm just running interactive workloads? The answer is yes. So in this test by MIT researchers, they ran memcache alongside a garbage collected workload. You can see in the top graph, the memory bandwidth on the machine was relatively low throughout the experiment until the mark phase of the garbage collector, where memory bandwidth saturated, basically went to almost 100%. If you look at the latencies at the bottom, the P99.99 99.9 percentile latency was very steady at around 50 microseconds, but then increased more than 3 orders of magnitude, 1,000 times during the mark phase. So yes, you don't need to run these big data analytic workloads next to your machines in order to experience noisy neighbor. Even garbage collection can be noisy neighbor. Or if you have a system that occasionally reads and writes a lot of data, that would be a noisy neighbor. But even if you don't trust this was kind of engineered just 2 processes. Does this happen on Kubernetes? So we ran the OpenTelemetry demo on a Kubernetes cluster, and we chose the OpenTelemetry demo because it has around 20 services written in 11 different programming languages and simulates an e-commerce website, which is something like what you might see deployed on Kubernetes. To measure the slowdowns when you have interference between applications, we used this very common metric that it's worthwhile knowing about called CPI, cycles per instructions. It's just the ratio of the number of cycles that the application used to the number of instructions that it used. And the idea is this. Let's say your application wants to execute some number of instructions. Then If there is high contention for memory, your application doesn't have its data in cache, it has to go to DRAM, then it's going to take a lot of cycles to execute these instructions. So it's going to have a high ratio, high cycles per instructions. On the other hand, if the system's really fast, everything's in cache, then to execute those same number of instructions, you need much fewer cycles, so the ratio would be lower. And so measuring this and comparing the high bandwidth conditions with the median, so you took all the times when the system was in high contention versus the times when it was in around the median, between 45 and 55 percentiles, you can see these types of slowdowns. Most of the services in the OpenTelemetry demo exhibited between 20 to 30% slowdowns. And there were some that exhibited up to 3 times slowdowns, specifically here Java and Python. And not to say that Java and Python are always terrible and what's on there, the product catalog is in Golang only 12% or 7%. Not to say that it's always this way, but in these systems and these implementations, you have these slowdowns. I don't know if this carries to yours, but these are massive, right? If you could shrink your P95 or P99 by these amounts, that would be a good gain. But should you really care about reducing these? I mean, whatever, a little bit more, a little bit less, does it matter? Well, here are simulations of 2 systems with kind of these garbage collection events that saturate memory bandwidth. And you can see a system under low load has fewer of these events. A system under high load has many of these events. And intuitively, if you look at these, which one is going to have better P95 or P99? Which one is going to have better performance to users? Obviously, the low load one, right? And we've kind of been programmed, like when we have SLO breaches, when our P95 is high, we scale out our systems. We move from the high load to the low load case very intuitively. So let me say it a different way. We have a problem where high load causes these memory contention events. Those in turn cause low CPU efficiency, right? The application data gets kicked out of cache and you have to go to DRAM, which is slower. And application service times suffer, so we breach our SLOs. And what do? How do we mitigate? We scale out. And I want to claim that this is an anti-pattern. We shouldn't do this. This is wasteful and ineffective. We're left with a lot of systems running at low utilization, at the 20 to 40%, rather than the higher utilization. What we really want to do is tackle the CPU efficiency. Make sure that these contention events don't reduce the efficiency of the system. If we can do that, then maybe we can get similar efficiency gains as the hyperscalers, right? Like if they have it, why shouldn't we? Shouldn't everybody be able to get those? And other than just cost of reducing your footprint, so you pay less for infrastructure, there's also the customer experience. Because if you think about it, when we move from high load to low load, we haven't eliminated these bad events, right? If we monitor P95, then we kind of push all the bad experience to the P96. We still have P96 terrible percentile, but we have good P95, which is what we measure. Are we done? No. So how can we get better performance for our users? If we can solve this problem, we'd be able to get better performance. All right, so what can you do about it? How can you make your systems better? So if we can only find the top 5% of pods that are the biggest offenders, then we can focus our efforts. There are some failure modes that we can mitigate today just by having good observability. One thing we could do is to adjust resources. So one failure mode, which is specific to garbage collection, is if you try to squeeze down the memory of garbage collected program too much down, then the heap space that it has a fixed cost, and then it needs some space for the heap to process transactions. If that space is small, then that pod is going to go to very frequent garbage collections. So by finding those, increasing the memory requests for those, you can increase their performance, decrease their saturation events and their noisiness. If you have programs that do a lot of scanning through data, right? Either garbage collection, but not garbage collection, right? If you have systems where just the programmers took on some tech debt, instead of using the hash tables, they scanned through a large data set. It takes a few milliseconds. Who cares? Well, the system cares. You can work with developers to optimize those pods. And if you don't have access to developers and you want a quick fix, you can always take these 5% of the worst offenders and put them on isolated infrastructure. Just get another node pool, put them there, and then all of the other service, 95% of the pods, are not going to have such high percentile latency, right? You can get a lot of gains just by isolating the worst offenders. So just having observability enables us to mitigate a lot of the problems. I'm excited about automatic mitigation as well, where we don't have to manually interfere. And there are mechanisms that allow us to get this type of control over offenders. One of them is modern CPUs have support for directly controlling how much cache and how much memory bandwidth each processor thread gets. The operating system tells the CPU how much is available on context switches. So this is available on some CPUs, many of the high-end CPUs. But even if you don't have support for this, there are many things you can do, like isolating the offender workloads on a few cores and then reducing the frequency of the cores. If the offenders don't have the cycles in order to generate noise, they can do less damage on the system. I get this question a lot. We're dealing with containers. Containers should do this, right? You know, containers isolate. Well, it turns out they don't. Just they haven't been built this way. Containers are a software delivery mechanism and they have security isolation guarantees, but performance is still lacking, right? Like we give them CPU and memory limits, but we don't give them memory bandwidth, we don't give them networking and so on. But these mechanisms to control cache and memory bandwidth are available in the Linux kernel. So there is a system called res control or resource control that you can configure using the file system. So we have mechanisms. What we can do is we can find the applications that are using a lot more than their fair share, the noisy neighbor, and then move them into these restricted sandboxes where they can't do a lot of damage, at least for the length of period of time when they're being very noisy. And in fact, our hyperscalers, the big ones, and not the big ones, but some hyperscalers have implemented this. Google published as early as 2013 that they had a system based on CPI, the cycles per instruction metric, deployed to all of their shared clusters to mitigate noisy neighbor. And Alibaba in 2020 published that for over 2 years, they've had around 1 million cores with this system in place. One of the major challenges of building solutions for this space is that events that hurt memory performance happen at very fine-grained timescales. So on the top here is a simulation of a system where you measure bandwidth at 10 millisecond granularity. And on the bottom are the same measurements averaged over a second, sampled over a second. So you see that all the signal is lost if you try to measure at 1 second granularity. And all of our existing monitoring systems are basically, all the metric systems are based on 5 minutes aggregations, maybe 15 seconds, but 15 seconds don't make sense here. So we set out to build a collector that samples, that is able to get observability into memory bandwidth at 1 millisecond granularity. So at this point, I'm going to switch to talking about the open source collector. We set out to build a collector that works at 1 millisecond granularity. You want to get these measurements across every core on your virtual machine every millisecond. And ideally, it would look like this. Everything would be aligned and great. But what you actually get in practice is this jitter. Jitter is bad because then every core measures a slightly different interval, and you can't reason about a full millisecond slice. Like each measurement is a slightly different interval. So you get these fuzzy boundaries between intervals. And so we set out to ask, like, can we really build a system that captures metrics at 1 millisecond granularity? And it turns out you can. So these are the jitter numbers. What are the fastest core to answer the timer to the last core to answer a timer? This was a 96 core machine. So you need to have all the 96 core machines answer during a small period of time. And you can see most of the cores answer within 5 microseconds. So that's a pretty good, pretty low jitter. We ran some stress tests there. The kernel comes with some very, very aggressive stress tests so that when kernel developers change code of the kernel, they can test the different subsystems. Here you can see there's one very aggressive stress test, kernel stress test called the lock stress, where half of the measurements were terrible at around 200 microseconds. So that's 20% fuzz jitter. Don't expect your systems to run with that type of load. Still, 40% of the intervals were good. So you could use that. You can still get a signal in a system under that load. Even the other load tests, there you can get 99% of these 1 millisecond intervals at under 50 microseconds of jitter, and we're talking about 1,000 microseconds, right? A millisecond is 1,000 microseconds, so 50 out of 1,000 is still really good for 99% of the intervals. This is completely usable. In regular systems, you get just 0.01% of intervals have more than 10 microseconds of jitter there. So this is, you can definitely build this. And we built it. And so here are some samples. This is a 500 millisecond span of time of this OpenTelemetry demo. You can see the different colors are the different components of the system, the different processes running in the OpenTelemetry demo. And here you can see an aberration. You have the OpenTelemetry collector suddenly bursting and using a lot of memory bandwidth. Now, if you move this graph to the top here, this is DRAM bandwidth. Now let's look at cache hits in the system. So this is, the memory that doesn't go to cache and the memory that goes to cache, that is fulfilled from cache. You can see there, that event probably looks like it evicted other applications from the cache. So those applications have a lot less cache misses, right? This is just, you can just see how the applications would slow down and have to access DRAM instead of going to caches. Right now, the status of the project, we've built basically the collector that has 1 millisecond granularity measurements. You can get these raw measurements in Parquet format into your object store like S3. And we're currently building in the next few weeks, over the summer, we're planning to develop these detection algorithms that say which intervals have a noisy neighbor kind of reduction in performance. So that we can attribute, say, okay, this is the noisy neighbor that caused this behavior. And so expect that soon. And the output from that is once you have that, you can say, okay, this service was noisy this % of the time, which is what we wanted for mitigation. And with the same data, you can build automatic mitigation, where at 1 millisecond granularity, you can say, okay, do we have a noisy neighbor now? Do we have a noisy neighbor now? Okay. If we do have a noisy neighbor, let's mitigate it. Let's move it to a sandbox, for example. The collector uses around 300 megabytes of RAM, so that's the memory request. 350 is what we request for it in the Helm chart. And we've benchmarked its utilization, so overhead, right? Every time you have an observability solution. So on the top here, you can see the collector's overhead in millicores. So you can see it arrives at around 200 220 millicores, and on the bottom is the system's utilization, the other programs running on the system ending up at 30,000 cores, so it's around 0.75% of CPU overhead. But I want to make the point that overhead almost doesn't matter if you can use this data to mitigate noisy neighbor. So let's go through this example. So let's say you have a system with a P90 with an average latency of 40 milliseconds. If I told you that latency, the average latency, would increase by 5%, right? We were talking about 0.75%, right? If that could increase by 5% to 42 milliseconds, but you would decrease your 95th percentile from 250 milliseconds to 75 milliseconds, I think a lot of folks would say, yes, let's do this. This is a very good trade-off to have. So, overhead is going to be low, almost doesn't matter. The Helm chart is available. The project publishes a Helm chart if you want to deploy. There's more details in the README, or please reach out to me. This is the project's repo on GitHub. It's licensed under Apache 2, open source. And I'd like to invite all of you to join and collaborate on the project if you're interested. We have work in eBPF and in Rust, which is the collector. We're building these benchmarks. We want to reproduce the noise tests that I showed, like Google ran, so that everybody could run similar noise tests in production. We're doing the data analysis for the detection of reduction in performance, the thrashing behavior that I showed you in the last slide. And if you just want to run the collector, please give us feedback, and we're happy to improve it. You can reach out to me and the team. There are contact details on the README, on CNCF Slack. Everything's there. So I hope this would get us to the better efficiency that the hyperscalers have and increase the performance that we give our users. And I hope we're not in this is fine mentality anymore, where kind of you have all this noise around you, everything's burning with noise, and performance suffers. So with that, thank you for coming to the talk, and I'm happy to take questions.
Thank you for this amazing talk. Who has a question? Come on, guys. It's already an experience to talk in this cube. So don't be shy. There.
Thanks for that talk. That was really nice. Both I and my colleague really enjoyed it. We're wondering, if you run on one of these clouds like Google or Alibaba that implement this, are you already, I don't know, CPI safe? I don't know what to call it, but we run on AWS. Are we already optimized, or do we still have to pay a bunch of money to get the millisecond metric?
Great question. As far as I'm able to read these papers, these papers state that these two companies deployed the solutions internally for their own use. So when they run their workloads, when you go to Google search, it seems like they would benefit from the performance and cost reduction, performance increase and performance reduction. But this is not available to users of the public cloud. And in fact, I've talked to several of the major cloud providers, including AWS, and I don't believe they're vague about it. They don't want to say they don't implement it, but there's no evidence to show that they do. And in fact, I have another graph that I show in other talks where you can see the difference. I showed the jitter in the 96 core machine, but you can get a 4-core slice on a similar hardware, and that has a lot more noise. It's still acceptable for the 1 millisecond measurements, but you can see the noise in a shared system. So I believe you don't get the benefit. Good question.
All right, thanks.
Hi. I have a question regarding the data, because you shown the jitter, the overhead of the collector. I'm wondering about getting the data out and analyzing it, because if you increase the granularity by 1,000, then you get from 1 second to 1 millisecond, you get 1,000 times more data. And I'm wondering, do you run this all the time? Do you enable this for problematic, enable this periodically and analyze what's the data volume? Is getting the data out even a problem?
Great question. So the question is, is this going to be too much data to even store? How do you get that data out? And should you run this continuously? The current implementation where you can get detailed data in Parquet, we don't expect folks to run it continuously. The idea is in the next version, once you have detection, you would output aggregate metrics, and those metrics don't have to, the system would measure at 1 millisecond granularity, analyze it, and then say, okay, then aggregate those results over time, saying, okay, this pod was noisy neighbor this % of the time, which are a lot less volume of metrics, and that you could use day to day. This is more if you want to get an in-depth view, a profiler view of the system. It's very useful to us because you really, when you develop these types of algorithms, you want to have a very good understanding of how the data looks so that you don't have, these nulls or zeros and you don't collect some stuff and you have jitter. You really want to look at it out of the box. So that's what you would use it. The current collector has limits. Usually, okay, so you asked about overhead. You can have, it depends on the system, you can have between 1 and 10 megabytes per second of data if you're in a big multi-core system with a lot of, well, maybe I'm overdoing it with 10. I think there are benchmarks on the website and you can look at what we found. Sorry that I don't remember out of hand, but it's a few megabytes. Let's call it a megabyte per second. The current collector has quotas where you can tell it, write a gigabyte and then you're done. And so that's what you would usually do, and that's how we run it. Thank you for the question.
Thank you.
You mentioned that one of the mitigations is to put the noisy neighbors into a node pool dedicated for that. Doesn't that make the performance of the bad the bad neighbors much worse? Even if you have this well-behaved node pool, you have all of the bad ones together. Isn't that counterproductive?
So I think you're asking is, if you isolate all the bad performers on one node, are they going to suffer a lot more than they should? Maybe they would. I'm not sure about this. Maybe we should follow up after. The idea is, if you have noisy neighbors that contribute, let's say 6% of the time they're noisy, and you have others that are practically never noisy, everybody else is going to suffer 6% of the time being noisy, those other pods being noisy. If you put all those on other systems, then maybe they suffer their 94th percentile, right? Like 6% of the time they're noisy. There is a point where if you squeeze them down to less infrastructure, now they're noisy even more. But maybe those services don't care for performance much anyway. It's a good question. Should follow up later.
You mentioned during the talk that there were mechanisms by the Linux kernel to specify some cache bandwidth restrictions on processes. Do you know of any initiative to apply that to Kubernetes and CRIs?
So if you're asking about an initiative to apply these to Kubernetes, we're trying. This is the goal. If you're asking about statically allocating resources, that is considered a bad solution. The problem is that you kind of want to have some pods use more resources when there's no other demand. You want to be what's called work conserving. You don't want to say, okay, I'm going to give 20% to this, 20% to that, 20% to that, and then somebody wants 40 and somebody wants 0. You want to grant that behavior to get the better performance. So static works and has been used in, as far as I understand, telco and high frequency trading, where you really need predictable performance. But I haven't seen any Kubernetes deployment that wanted to use it.
Cool. Thanks again, Jonathan, for this amazing talk.